welcome back. We in the last lecture we were trying to see that if we consider f minus s and f, then how this is going to behave with any other trigonometric polynomial of degree less or equal to n. Then by writing it out, we have found that f minus f s and f inner product, this is 1 by 2 pi minus pi to pi f of x, and then this is p x bar dx minus because s and f is f hat of n e to the power n x, it is a finite sum. So, we pull out both the sums, then we have got f hat of n alpha k bar minus pi to pi e to the power I n x into e to the power minus I k x. This also we take this out, mod k lesser equal to n, and then alpha k bar is scalar, we get that out, minus pi to pi f of x e to the power minus of I k x dx. This is nothing but f hat of k, and here 1 by 2 pi, and then this, if n is not equal to k, by the orthogonality of this, this is going to be equal to 0. So, now out of these two sums, this integral is going to survive only when k is equal to n. So, when k is equal to n, this becomes 1. So, minus pi to pi integral is 2 pi. So, 1 by 2 pi gets cancelled. So, what we can here get is summation over mod k lesser equal to n, this alpha k bar, and then f hat of k, because n equal to k, this is going to survive. Now, this 1 by 2 pi minus pi to pi f of x e to the power minus I k x, this is nothing but f hat of k. So, this is lesser equal to n alpha k bar f hat of at k minus So, this is very important for us, because now f minus of s n f is orthogonal to every trigonometric polynomial of degree less or equal to n. So, in other words, we will just rewrite it is orthogonal to p, where p is a trigonometric polynomial of degree less or equal to n. Okay. So, now when we have the notion of orthogonality, then the first thing comes to mind is to ask whether something like analog to Pythagoras theorem is true or not. So, as a matter of fact, what we can see that this Pythagoras theorem, let f is orthogonal to g, then norm of f plus g square, this is equal to norm of f square plus norm of g square. So, if they are orthogonal, then this square is equal to this square plus this square, because this is going to be the addition of this and this. Okay. So, we will start with the left hand side, f plus g square. This by definition, this is f of plus g inner product of f of. By the linearity of the inner product, we just take f plus f g plus g f plus g g. Now, this is simply is norm of f square plus norm of g square. Okay, so everything fits in whatever we have learned in our Euclidean setting and the inner product in linear algebra. So, in this space is a cube with an inner product which is given by this. So, now one of the so our aim is to look for that norm of M f minus of S and f, this goes to 0. This is what we are going to prove. This. So, now, so this what you can see that if we are saying that the norm is essentially some distance, then this is S and f itself is a trigonometric polynomial. Now, my f is a function. So, now I am trying to get the distance between f and S and f. So, in other words, I can ask that is it this distance, is it comparable to the distance between f and any other trigonometric polynomial of degree less or equal to n. So, that is what is our main observation. So, this is a proposition, let P be a trigonometric polynomial of degree less or equal to n, then norm of f minus of S and f norm is less or equal to norm of f minus p. So, in other words, what this says is that the S and f is the closest, is a trigonometric polynomial of degree n which is closest to f geometrically. So, and this is so now we will prove this. Now, let us look at norm of f minus p, let p of x, this is equal to summation over mod n less or equal to n alpha n e to the power I n x. That is how the p is going to be look like, and some of degree less or equal to n. So, now this is equal to, what I can do is that this I will write f minus of S and f plus S and f minus p to norm. Now, look at what is our S and f. S and f is a trigonometric polynomial of degree n. Now, S and f minus of p is equal to summation over mod n less or equal to n f hat of n minus of alpha n e to the power I n x. So, this let me call this as q x. Now, S and f minus p, this is again a trigonometric polynomial of degree less or equal to n. Therefore, this is going to be, so this again let me rewrite S n of f plus q As we have seen here previously, that f minus of S and f is perpendicular to q. Therefore, by Pythagoras theorem, both square is both the sides. So, this is f minus of S and f plus, and norm of q is a non-negative quantity. So, norm of f minus p square, this is equal to norm of f minus of S and f square plus a non-negative quantity. This will imply that so, in other words, that is what we have proved, that in the language of the approximation, this S and f is among all the trigonometric polynomial of degree less or equal to n, S and f is closest to f in terms of this norm. Okay. So, now we are ready to prove the main theorem. So, which is that let then 1 norm of f minus of S and f 2 norm, this goes to 0 as n goes to infinity. In other words, what we are saying, the partial sum converges to f in the mean square. So, and secondly, we will get that norm of f 2 norm is equal to summation over n varies over z mod of f hat of n square whole to the power 1 over 2. So, which means in terms of the norm of f, we can completely capture, if we know f hat of n, we can completely capture through this the norm of f. So, this is the so called little L 2 norm, but we are not going to talk in the abstract setting, but this is known as the Parseval identity, and which is one of the cornerstone of the Fourier series. This is very satisfying and one of the most fundamental and important result in Fourier series. Okay, so what do we know about the trigonometric polynomial and vis-a-vis the role of f? So, when we proved the Fayer's theorem, there we have seen that if f is a continuous function, then f can be approximated uniformly by a trigonometric polynomial. So, in other words, from Fayer's theorem, we know that if f is a continuous function, 2 pi periodic function, then for every epsilon positive there exists a trigonometric polynomial P such that norm of f minus p infinity, which is equal to supremum of x belongs to minus pi to pi mod of f of x minus of p of x, this is less than epsilon. This is what, because just think about that f convolution of the fair kernel, that is going to be a continuous function and it is a trigonometric polynomial which approximate f uniformly. Okay. And now let us look at the what here I am defining. So, now suppose f is in Riemann integrable, observe if f is Riemann integrable minus pi to pi, then to norm this square, this is equal to 1 by 2 pi minus pi to pi mod of f of x square dx. Now, if I pull out the supremum of f from the integral, then this is going to be less or equal to f infinity 1 by 2 pi into 2 pi, which is equal to 1. So, this is square. If I am pulling it out, then the square term is going to get pulled out. So, therefore, what we have got is that norm of f 2 norm is less or equal to norm of f of infinity norm. Thus, here what we have for this particular p, this is also again less than epsilon, because it is going to be dominated by the sup norm. Okay. Now, so now let us assume, let the degree of this p is equal to m. So, therefore, if I choose in my Sn, if n is greater or equal to m, then p is a trigonometric polynomial whose degree is less or equal to n. Therefore, what we have found in our earlier observation in the proposition, Sn of f 2 norm is less or equal to norm of f minus p 2 norm, and which is again less or equal to norm of f minus of p of supremum. This is less than epsilon by the fair theorem. So, by proving that Sn f is the closest trigonometric polynomial in from all trigonometric polynomial of degree less or equal to n, we have arrived that f minus of Sn, this will imply what? F minus of Sn of f 2 norm, this goes to 0 as n goes to infinity. Okay. So, now let us come to proof the second part. So, we would like to prove that norm of f 2 square is nothing but summation over mod of f hat of n square. So, for that let us look at norm of f squared, this is equal to f minus of Sn of f plus Sn f square. Okay. Snf is also a trigonometric polynomial of degree n. Therefore, by Pythagoras theorem, we have f minus of Snf square plus norm of Snf square. Now, as we can see that norm of f 2 is equal to limit n goes to infinity norm of S n f square, because already you have proved that f S n f converges to f in the mean square in the 2 norm. Therefore, this happens. So, let us just calculate what is our S n f 2 square. This is by definition S n f, S n f. So, writing down this is minus pi to pi summation over mod n lesser equal to n f hat of n e to the power I n x into summation over mod k lesser equal to n f hat of k bar e to the power minus of I k x dx, which is all these are finite sum. So, we will pull this mod of n lesser equal to n, then this sum mod of k lesser equal to n, f hat at n, f hat at k bar 1 by 2 pi minus pi to pi e to the power I n minus k of x dx. So, now the orthonormality of e to the power I n x tells us that this k sum is going to survive only when k is equal to n, otherwise this is not going to survive, they will be killed, they are orthogonal, pairwise orthogonal. So, this amounts to, now k is equal to n means this is f hat of n, f hat of n bar. So, this is mod of f hat of n square. So, now hence this the limit is going to be, and this is this is a monotonically increasing sequence which is bounded above, therefore, the limit is going to exist and this limit is nothing but going to be norm of f. Thus, so this is one of the most important result in this subject. Okay, so, we can easily, once you have this, then as you can see that here we have assumed only f is Riemann integrable, hence f is a bounded function and so on and so forth. But this there is a technicality. So, here we have proved this. So, if we go back to the other one, even in the first case, we have proved that if f is a continuous function, then f minus of S n f, this goes to 0 in the norm. Now, if f is not a continuous function, we know that there exists a sequence of continuous function which converges to the Riemann integrable function f in the square norm. So, because it converges uniformly, hence the square norm is dominated by this. So, it converge, as we have seen that this is going, just as you can see the way we have proved that there exists a sequence of continuous function which converges to f in under the integral sign. Exactly by following the same argument, we can say that if f is Riemann integrable, then there exists a sequence of continuous functions as f n, such that f n minus of f 2 norm is less or equal to goes to 0. So, what I am saying, if f is Riemann integrable, then there exists a sequence f n of continuous function such that as n goes to infinity. So, once we have this, then with the standard argument we can prove this result for f is a Riemann integrable function. So, now let us see the corollary, some of the interesting corollary of this. It has many application. So, one trivial corollary is that when we are saying that f without getting, we can get this, because if f is Riemann integrable, we know that summation over n varies over z mod of f hat of n squared. This is finite, which is equal to norm of f, which is a finite number. So, hence now this is a f hat of n square is a convergent series, therefore, the nth term will go to 0, that is Riemann-Lebesgue lemma. This is another way to prove the Riemann-Lebesgue lemma. And now, let us ask ourselves, what we have seen is that if f is twice differentiable, then f hat of n is mod of f hat of n is less or equal to some constants by mod n square. And so, hence the Fourier series converges, and by the Fair theorem, because it is converging absolutely. So, it is going to converge even pointwise to f of x. Now, if f is in C1, what we have noticed is less or equal to some constant by mod n for n not equal to 0 for large n. So, now it is natural to ask that if f is C1, then can we conclude that the partial sum converges to f everywhere pointwise? Certainly, this decay condition is not going to give us the convergence, because we know that 1 by n series it does not converge. Now, this question we will address in the next lecture, and we will see that if f is in C1, that means f prime exists and f prime is continuous, then what we are going to get is that the Fourier series converges. That is what we will prove in the next lecture. Thank you.